whiteboard that I often use for this class. And before we start, I like to sort of review the material that we have been discussed so far in the past, and that is let me see. I think I like to pin this class. Okay. So yeah. So this is the topic that we discussed. Is last time 2.1. Car park on the level roads and on the inclined road. And we solved this problem very easily by using a free body diagram where we draw a simple model of vehicles, including the axis of X and the axis of Z, including the location of the center of gravity and the gravity forces here, and the normal force on the front wheel and the normal force of the rear wheel, and also the distance between the center of gravity to the front tires and to the rear one. And by using this free body diagram, we were able to sort of drive the normal force FZ1 and FZ2, right? So FZ1 essentially is the half of the car weight. This half of them multiply the ratio of A2 divided by L, right? That is for inclined roads, and we also discussed for the that is for the level road, and we also discussed for the inclined road. And in this case, we discussed three conditions by using a rear brake, front wheel brake, and also a four wheel brake. Okay, so by introducing the brake, then we can stop the vehicle in an inclined road, and as a result, we are able to sort of derive the force on the front and on the rear, and essentially the same with level road plus the angle, right? Plus the angle. And we also discussed the stability conditions, and for the vehicles parking at a certain angles, tangents pi m, where pi m is equal to A1 multiplied by mu divided. And this is the conditions of a maximum friction. This gives us the maximum angle of the road where you can brake, where you can stop without moving. And those are the things that we discussed last time. And now we are going to continue our discussions to something with acceleration, right? Let's discuss here. Okay, so today we are going to talk about vehicles on the condition of accelerations, right? So let's start for today. We're going to talk about 2.3. Yeah, we are going to talk about 2.3. Maybe I'm going to increase the thickness a little bit, which is accelerated car on a level road. So we are going to discuss about some accelerated car, right? So accelerated car, we're going to discuss about accelerated car on a level road, right? On a level on a level road, right? So our intentions is to sort of develop the equations for we like to know what is the force of FZ1, how big it is when the car is accelerated, and we also like to know what is the FZ2 when the car is accelerated. And we start with a very simple free body diagram here. So let's start with a free body diagram. Yeah, we start with the free body diagram of the vehicle, and as you saw that we are going to draw a very simple vehicle in here, and this is the front side and this is the rear side. Okay, so this is the front side of the vehicle, and the center of gravity is located here. This is the center of gravity, and the x-axis is pointing to these directions, and the z-axis is pointing to these directions. And the location of this center of gravity to the center is we call it as a A1 to the front wheel, and to the rear wheel we are going to call it as a A2. And I better remove this one first, and we are going to call it as a A2, right? This is the z directions, and this vehicle is moving at the certain accelerations a to the front. This is the accelerations. Okay. I think I'm going to write it down here. It is the accelerations. Okay. As it's moved with the accelerations to the front, then it will produce an inertia force. So the inertia force will be this way, right? This is the inertia force. Okay, so that is the inertia force. So remember that we got to make a note here. We write a note that the inertia force is opposite. Is in the opposites of movement. Okay, so I think this part is kind of important for you to remember that the inertia force is always in the opposite directions of the movement. So we have an inertia force in this direction, and clearly back here, down here, we have a normal force in the z directions. We also have a normal force at the front wheel, and here we got to multiply by 2, right? We got to multiply by 2. Now, for this vehicle to be able to move at a certain acceleration, then we need a force that pushes forward the vehicle, and this force may be coming from the engine. And the force directions, we're going to call it fx2, and also we'll multiply by 2 because we have a 2 wheel. And similarly, we have fx1 here, and we also multiply by 2. Okay, so this is the free body diagram, the free body diagram, and now we are ready for let me see. Okay. We already have the free body diagram, and the first is we have a set of equilibrium equations. So in equilibrium conditions, let's say equilibriums, in the equilibrium conditions. So for equilibrium condition, we have a sigma fx should be equal to 0, right? So all the forces should be 0, and we also have uh, all the forces in the x and also in the z direction, right? In the z direction should be 0, and we also have a sigma moment should be equal to 0, right? So all the forces and it should be equal to 0, right? Now this one, yeah, this one give us that two fx1 here and plus to the positive side, right? 2 fx2. It should be equal to this. Should be equal to the inertia force, right? And this one also give us a very simple conditions that the two fz1 plus 2 fz2 should be equal the weight of the vehicle. We assume the weight is going down here. This is the weight of the vehicle, right? So as you can see that the governing equation is the governing equation is it's a very simple governing equation. Now let's take this moment at the point C, right? And the point C is located here, right? This is the point C. I'm going to set it to 0. So I'm going to get another simple equation here. So I can see that 2 fx1 and plus 2 of fx2 multiplied by the height of this of the vehicle. That is the height of the center of gravity, right? Let's say we take a positive side in this way, and all of them, if we multiply by h, right? Multiply by h gives a positive moment here, and plus plus, say, let's say a1 multiplied by 2 fz1 should be equal. I'm going to move it a little bit around. Yeah, let me clean this part first. Yeah, it should be this one. It should be equal to this this moment, right? It should be equal to a2 of 2 fz2. It should be equal to that, and it's not difficult to see that we can rearrange this all the equations, and I'm going to simply see this part, right? I think I'm going to write it down here. As you can see, this part is actually the same with this equation, and essentially it is a MA, as you can see up here. So I can sort of rearrange this, make it much more simple, and that is, I can simply write it down as a 2 fz1 and a1, right, and minus, right, 2 fz2 2 fg to a2, right? This minus this equal, right? Minus this equal minus m and a and s, right? So from this term and moving to the other side. Okay, so that is the equation we obtained so far, and I like to put a number to this equation because it makes things easier if we have a number. Right? I like to have equation 3, and now we can we can clearly see that we can combine these equations, equation 2 and equation 3. We can combine them to sort of eliminate fz and f1 from here to obtain fz and m1. Okay, so what we are going to do now is to equation number 2. We are going to multiply by a2, right? We're going to multiply by a2. So as a result, I'm going to have a 2 fz1 a2. This one, I'm going to multiply this by a2, right? So this one multiplied by a2, this one multiplied by a2, and this one multiplied by a2. So as a result, I get 2 fz2 multiplied by a2 equal the m and g and a2, right? And sort of now I can do a simple addition, right? So if I add them together and this part will be eliminated. So I only have this part, right? And the a1 plus a2 is equal L. And remember that a1, right? I'm going to increase the size a little bit. Yeah. So the a1 plus a2 equal L, right? So if I sum this one up, and then what I'm going to have is a 2. Okay. Let me see. Okay. Okay. Let me clean this first. It's a 2. Yeah. Okay. So I think if I sum them up, I have let me see. This is M and A. Oh, I think I need a 2 here, right? I need a 2. Sorry. This one is M and A. Oh yes, M and A already. And yeah. Let me sum them up here. So if I sum them up, I have M and G and A2, right? Minus M and A, right? And H, right? I have this M, A, and H, right? It's a positive here. Let me check it. I think I make some mistake here. Okay, so I have a 2 z1 multiply by L, right? Okay. So as a result, I can write it down here. That's fz1 equal 1/2 of mg a2 divided by L, and minus 1/2 of m and a I think yeah, M and A, um, and H, right? And H, let me see. Okay. And H divided by L. Okay, so this is one of the sort of important formula that we have, and so as you can see that the force, this is the static force and this is the dynamic force, right? Um, yeah. So you can imagine this part. You can imagine this part as the static components. This is the static component, and you can imagine this as a dynamic component. Right? And it is not difficult to see that Fz2 is equal this mg mg A1, right? And mg A1 divided by L plus 1/2 of MAH divided by L. Okay, so this one for the force that acting at the rear of the vehicle, right? So the force at the rear is become bigger with acceleration. So if I draw the vehicle again, for example in here, and this is the vehicle, and because the inertia force is in these directions, which is M and H, and so it produces a much more bigger force in here and than in here, right? So this one is FZ2, and this one is FZ1. So the force on the rear wheel is it's much bigger than the one at the front, right? So this part I think is it's not difficult to understand. So now next, what is the maximum acceleration that we can achieve, right? So let's talk about that. Yeah, let's talk about the maximum accelerations that we can achieve. Okay, so now we're going to discuss the second issue is the maximum acceleration on a level road. What is the maximum accelerations on a level road, right? On a level road, and so first we are going to we have three cases here, right? The cases that we need to talk about is the case when you have a four-wheel drive, right? We have a four-wheel, we have a rear wheel, and rear wheel, and finally we are going to discuss about the front wheel drive, right? We are going to discuss about front wheel drive. Front wheel. Okay, so we start first with we start number one with the four-wheel drive, right? We are going to start the discussion with the four-wheel drive. Okay, so that will be the first thing we discuss is the four-wheel drive. So in the case of a maximum, in case of the maximum accelerations, we assume that that the max that the force on the wheel has reached the maximum tractions. Okay, this is the this is the maximum maximum tractions on the wheel. This is just before sliding. Okay, this is the maximum force that the wheel can produce without sliding. Okay, before sliding. Okay, this is before sliding. This is just the car before sliding, and that is the this is the front side, and because we have a four-wheel drive, and we are also going to have one more formula for the this is for the force from the front vehicle, right, from the four-wheel. So the force produced is from all the wheel we have, right, the one from here and the other one from here. So we have fx1, and we have here is fx2, right? Okay, and so the equation of motions before, yeah, the equation of motion, you can use plus and minus because it may be for acceleration and deceleration. Okay, acceleration and decelerations, and the equation of motion before we have that's ma equal ma, I think equal 2 fx1 plus 2 fx2, right? This is the equations of sigma x equals 0, and earlier we applied this thing, right? And we can substitute this to here. It's going to give us a very simple equation that is mu f z1 plus fz2, right? Plus fz2. Okay, so if you plus fz1 and fz2, as in the previous section we show that so if we take the term fz1 and fz2, if you say here fz1 plus the fz2, what you're going to cancel out this, and as a result you're going to have this, right? So fg1 and fg2 would be half of the m and g, right? Or half of the vehicle weight, right? Okay, because the total weight of the vehicle fz1 plus 2 fz2 is equal to total weight of the vehicle, right? Okay, so that would be we come back here, and so we are going to say that equal 2 and mu of weight of the vehicle, right? Is m and g, right? So now we have here the m and a, and we can sort of cancel out the and oh yeah, the two will be, the two also will be this one, yeah, this one too, it will be m then g. Okay, so I'm going to eliminate this one, yeah, because two of this will be m and g, right? And finally we have a equal plus minus mu and g. So or a divided g equal plus minus mu. Okay, so this is the maximum acceleration you can achieve if you have a four-wheel drive, right? If you have a four-wheel drive, and by using a similar approach, you can use a rear-wheel drive and also and a front-wheel drive, right? Okay, and in addition to that, you can discuss about let's say what about rear wheel drive, right? Um, rear wheel rear wheel drive, right? Let's discuss about the other condition of the rear wheel drive. So if the rear wheel drive, then the force at the front, and the force at the front will be zero. There is no force of the front wheel, and the only force we have is from the rear wheel, which is mu multiplied by f z2. Okay, and from a previous equations, you already know this fz2. So fz2 is given here. So this is the fz2. It is half of the weight plus the acceleration, right? So it's not difficult for us to see that the fz2, yeah, from previous work, we understand that we have this fz2 equal 1/2 of this of the weight a2 divided by l, sorry, a1. Okay, a1 divided by l plus half. We have you can sort of write down as m and m and a and h divided by l, right? Okay. So this is the equations you sort of you obtained earlier, right? You obtained earlier these equations, and now you are going to see these equations that can be written as m and a equal mu and fz2. Okay, so you can sort of put this one in. Yeah, you can put this one in, and finally you are going to get that the maximum accelerations divided by g equals a1's multiplied by mu and l's minus h mu, right? So this is the maximum accelerations, that you can achieve by the rear wheel. And if you have a front wheel, let's say you have a front wheel drive. You have a front wheel drive. If you have a front wheel drive, then the maximum accelerations by the front wheel is a2 multiplied by mu divided by L's and plus h multiplied by mu. Okay, so this is how you are going to get the accelerations. But although you have these accelerations, it's very important to discuss about a stability condition. Okay, a stability condition. This is very important part. A stability condition. Okay, and the stability condition said if we have this vehicle, if we have these vehicles, and we sort of accelerate here, or maybe we accelerate this way in the braking thing. This is acceleration, this is deceleration for braking, but we always avoiding this car from going this way or from going this way, right? So we avoid that. For the stability condition, we cannot decelerate such that this becomes zero. We cannot also accelerate or decelerate such that this fg2 becomes zero. Okay, so this will be the stability conditions. If this is zero, then the car will rotate this direction, right? Okay, because of the strong acceleration, the car will go that way. And in the other, if the strong braking happen, the car may go this way, right? So this defines the stability conditions. And I'm going to write it down here as a zero. So from the stability conditions, so we can use this equation very simple. So the for the front wheel, right? For the front wheel, yeah. For the front wheel, okay. So for the front wheel, we have this fz1 equal half of the weight multiplied by a2 divided by l, and mg h divided by l multiplied by a and g, right? So if we set this is equal 0 for the stability conditions, and then we can easily see that the maximum accelerations divided by this should not exceed a2 divided by h. Okay, this is the stability condition. Now, this is the stability conditions for the front wheel, and we also have yeah. So that is the most important part, right? Okay, so as you can see that you can drive your car to maximum accelerations. You can drive your car to the maximum acceleration, but the maximum acceleration should not exceed a2 divided by h, right? It should not exceed these stability conditions, right? Okay, so let me review again what we have discussed so far. Okay. Okay, so initially, yeah, we start our discussion with. So we start this discussion with 2.3, a car on a level road, and we are interested on the fz1 and fz2, and this is the free body diagram where inertia force is added and directing opposite of the movement. And from here, we obtain the force. Yeah, we obtain the force on each of the wheel, front and the rear, to be this, right? And we also analyze the conditions of what is the maximum acceleration can be achieved. And we have 3 cases: a four-wheel and the rear wheel, and the front wheel. And in case of the four-wheel drive, so the maximum acceleration is a divided by g multiplied equal mu. This is the frictions. And in case of rear-wheel drive, the maximum acceleration is a1 multiplied by mu divided by l minus h multiplied by mu. And for the front-wheel drive, the maximum acceleration given here. Whatever your acceleration is, you have to pay attention on the stability condition. And the stability condition said you can accelerate, but not reaching the level where fz1 equals 0. If the fz1 equals 0, then you have this acceleration. So this is the maximum acceleration for a stable driving. right? Okay, so now, so I like to give you a very simple um, assignment to finish. Let me see, presenting something else. Um, okay, yeah, hopefully you can see this. I'd like to give you a very simple assignment here where you must determine the time to reach 100 km per hour from zero. If your car is four-wheel drive and a rear-wheel drive and four-wheel, this is one is front wheel. And so the data of the vehicles, the wheelbase is 2,272 millimeter, and the height of the center of gravity is 220. Friction is 1. We assume that center of gravity is located at the center, and the G is called 9.81. So to solve this problem, you must compute maximum accelerations for each case. And from maximum acceleration, then you can sort of compute the time, right? I think um, it's not difficult for you to see that um, if you assume it to be linearly related um, between acceleration and velocity. So I believe that you already learned a simple equation in the high school that if the car has a constant, if a car have a constant accelerations, then we can estimate the next velocity from here. This one for a constant acceleration. For a constant acceleration, that the next velocity from initially zero can be obtained by this equation. So you can sort of compute the time based on this equation. And now let me get back to you for the problem. Um, okay, so here you go. Okay, now let us discuss further about the second topics, which is 2.1, accelerating car on an inclined road. As you can guess, the normal force is the same with the static components on an inclined road. This is the force acting when a vehicle parking, not moving on an inclined road, as given in the previous sessions. And when the car is accelerating, we have sort of additional forces acting on it, right? So we have half of the inertia force multiplied by h divided by L. And the rear wheel will receive a slightly bigger forces, as you can see in here. Okay, and this is the sort of the free body diagram for the case. So now let us also discuss the maximum accelerations for the four-wheel vehicle. So the force produced by the engine should be less than the friction force, right? And the same thing is also applicable for the front wheel and the rear wheel. So in total, as you can see, that the maximum force should not exceed the friction force. So we can easily drive for the four-wheel drive, then the maximum acceleration is plus minus mu x multiplied by cosine minus sine, right? And this case is similar with the previous results, as you can see in here, which is the maximum acceleration is equal mu times g, right? So this is the same result, except the difference is we need to take into account the angles of the road, which is cosine pi minus sine pi. And to avoid car from sliding, right? To avoid car from the sliding, the angle should not exceed mu x. And this requirement also exists when we analyze the car in parking conditions, right? So, however, the limit of accelerations, the limit of acceleration is given by fz1 should be greater than 0, right? And fz2 should be also greater than 0, right? And with that conditions, then we can say that maximum acceleration should be less than this, and maximum acceleration should be greater than this. So the acceleration should be within these margins. As you can see that if the accelerations goes to 0, if this component 0, and we have this static conditions, yeah, without accelerations. Okay, so now let's talk about maximum decelerations when the car taking a brake for a single axis brake, yeah. And we're talking about the condition that the pi equals 0, and we assume that the rear wheel force equals 0. So the car is using the front wheel brake, right? Front wheel brake. And with a similar approach, we can see that the maximum accelerations for this case is shown in here. Okay, so for the summary, now let's talk about the front wheel and the rear wheel for the parking conditions and parking on the inclined road, and acceleration on the level road and accelerated with on the inclined road. As you can see that on the parking on the level road, the force is just half of the weight, but when it is inclined road, then we have to take into account the angle of the road, right? And when the car is accelerated, we need to take into account these inertial components, right? And when accelerated on the inclined road, we need to take into account the angles and also the inertial forces. Okay, so this equation is much more complete than any of those above equations. So for us to obtain without acceleration, we can just set this to 0 without acceleration, and we get this back, right? Then if the road is level, we can set this one to 0 and this is to 1 and get this one back. So this part is the most complete equations. By having these equations, you can sort of derive equation for any other conditions, right? So this is the only most important equation that you need to write down in this case. Okay, so let me give you a few cases to solve here. Okay, so before you solve this equation, then please take a notes of a number of important equations, and I'm going to give it to you in this slide. Okay, so this is the equation for the maximum accelerations on the level road, right? And this one is the maximum accelerations when for the rear wheel drive. It should be check again the stability condition that the acceleration should not exceed this, and maximum acceleration for the front wheel, and similarly it should not exceed these stability conditions. And this is on the inclined road, the normal force in Z1 and Z2, and the conditions of the maximum accelerations four-wheel drive on the inclined road. This is the condition avoiding of the sliding of the car. And to avoid sliding, it should be within this angle, right? With this angle. And the maximum deceleration for a single axis brake is given here. If you have only a single axis vehicle. Okay, so please take your time to solve this problem. Um, you're asking to determine FZ1 and FZ2, and also FX2 if the car is parked on an uphill with a 30-degree angle and handbrake is connected to the rear wheel, right? So this is the case of the rear wheel braking system. And what would be the maximum road angle if the car can be parked, if the car can be parked if mu x2 equal 1? So to solve this problem, to solve this problem, then it's very important for you to use this equation, right? This equation is very important for you to be used, and as the fx2, you can draw the free body diagram, and for the maximum angle, in case of the rear wheel brake. So it should not exceed this. Yeah, it should not exceed this. If you have a four-wheel drive, but if you have only a rear-wheel drive, then the maximum angle should not exceed this, right? Okay, so from that, I think I believe that you can obtain the equation. Let me give you a simple illustration concerning consider the maximum parking angle. So just a moment, let me share to you, present something else. Okay, so now let's talk about the maximum parking angles. Yeah, let's talk about a maximum parking angle, right? About maximum parking angle. And so you essentially can park your vehicle. Let's assume this is the vehicle wheel, and this is the vehicle body. So yeah, and this is your vehicle. Let's say this is pi, and what you have to think about, if this is the center of gravity, if the angle is small, let's talk about the small angle problem here. And so if the angle is small, as you can see, that the weight of the vehicle directions is going this way, right? It's going this way, right? So the vehicle is pretty much safe, right? However, if the angle is going this way, yeah, this is the touching angle, and potentially your vehicle might be unstable and tilt this direction, right? So the maximum angle that you can park will be controlled by this direction. So the weight should go here, and this will be the maximum angles that you can park, right? So you have to think about this, and will be your pi, right? And this distance will be A2, and distance will be H. So for that reasons, the maximum angle before sliding. So for that reasons, the maximum angle before sliding yeah, the maximum angle before sliding happen is the tangent pi equal a2 divided by h. Okay, so this is how you get a formula. Tangent pi equal a2 divided by h. As you can see in the slides, let me show you the slide. Uh, okay, as you can see in here that okay, as you can see that the maximum angle should be less than a2 divided by h. This is the maximum angle that you can park your vehicle, right? So hopefully it's clear how you're going to derive these equations for the maximum angle. And now I'm going to give you this opportunity to solve this particular problem.